Next type of basic function I want to talk about, graphs with asymptotes. So I've drawn some random graph here to try and illustrate the different types of asymptotes that we can get. But basically, what is an asymptote? It's simply a way of describing the behaviour of a graph at its extremities. And I suppose I also should have put there, but also at discontinuities as well. So with this one here, what have we got? Well, a vertical one, there it is. So a vertical asymptote, that happens at when a curve is discontinuous at a particular point, but the limit of the function approaches plus or minus infinity at that value. And the one I've drawn, on one side it approaches minus infinity, and on the other side it approaches positive infinity. So that's a vertical asymptote. Now, functions will never cut or touch a vertical asymptote because it's a line of discontinuity. So if it's not in the domain, well then the curve can't be there. So we know it's never going to cut or touch that. Then we could have horizontal asymptotes. I've got one there. That's what happens when the curve's out at infinity, negative infinity. So the vertical asymptote, that's when y is going to plus or minus infinity. The horizontal asymptote, that's when x is going to plus or minus infinity. It doesn't have to be both, and the one I've drawn, it's only at positive infinity it's going to the horizontal asymptote. Then you get ones that are at an angle, so oblique asymptotes. Now, when will they occur? That's when both of them are going to plus or minus infinity, both the x and the y value. Now, the interesting one is, oblique technically means straight line at an angle. But of course, it doesn't have to be a straight line, the other type of asymptote. I mean, it might approach x squared, or it might approach some other function, and that's okay. Again, it's just telling you what happens as the x value is getting out of the extremities. So whatever it's approaching, the actual curve will start taking on the shape of that asymptote as you get closer and closer to infinity. Now, functions can cut or touch the horizontal ones or the oblique ones, and you'll notice I've got it cutting the horizontal one because it's just something for when the x values are going to plus or minus infinity. So when the x value is anywhere else, the asymptote's meaningless. So it can cut it, so hence why my one does there. The vertical can't. I guess the first type we see is this rectangular hyperbolic function, y equals 1 on x. Now, I don't know whether you knew it was called a rectangular hyperbolic function. You certainly knew it was a hyperbola. The reason it's called a rectangular hyperbola is because the asymptotes are at right angles. So any curve where the asymptote is at right angles, it becomes a rectangular. This one demonstrates inverse variation. So if you're playing with your data and you have inverse variations, you would expect it to take on this hyperbolic shape. So inverse, as one's getting bigger, the other's getting smaller, and vice versa. And again, every single rectangular hyperbola can be transformed from that basic one using translations, rotations, reflections, and so on. In fact, that one I talked about before, x squared minus y squared equals some number, that's obtained by rotating this one 45 degrees. And that's how you would get that one. So they all can be created from the basic 1 on x. Oh, I say 1 on x, of course you might see it written where the two pronumerals are multiplied together. Same equation, of course, xy equals 1. So how do you recognise a hyperbolic function? Well, you're basically looking for something like this. One of the variables is in the numerator of a fraction, and the other one's in the denominator of a fraction. You're probably going to get some sort of hyperbolic situation. I suppose the other thing to look out for is the two pronumerals are multiplied together, so that might indicate one as well. Exponential functions, another basic function we should recognise. So it depends what the base is, how the exponential is going to be oriented on the number plane. This is when the base is bigger than 1. So when the base is bigger than 1, we get our standard exponential, which starts shallow and then gets steeper and steeper and steeper as we go along. So that's when the base is bigger than 1. If the base is between 0 and 1, so over there I've said less than 1, but you don't have negative bases, So when it's between 0 and 1, it flips the other way around. So it starts steep and then gets shallower and shallower and shallower. So it goes the other way around. Well, recognising this one's usually pretty easy because you've got one of the pronumerals is the dependent there, and then the other one you see in the power. So why is it called an exponential? Another word for a power is exponent, hence the name exponential. As I said, the base has to be positive, and I guess it shouldn't be equal to 1. I mean, it's questionable. Is 1 to the power of x an exponential? I mean, you think about it, all you're going to get is a straight line because 1 to the power of anything's 1. Could we call it an exponential? Debatable. Okay.